Hi. Up to this point, we have made two derivations of the Schrödinger equation. The first derivation was the characteristic function derivation, and the second one was the entropy derivation. We have obtained from these two derivations a number of results. The last one was that the quantum mechanics is unequivocally uh, uh, connected to the notion of fluctuation. And with this new derivation, the stochastic derivation, we will show that these fluctuations are related to stochastic behavior. So in this video, we will show this derivation. This is a derivation that it is not mine. It was presented by Luis de la Peña and Ana Maria Seto, two Mexican physicists, and their approach is based on dividing the velocity c in two parts. One part is the systematic velocity v, and another one is the stochastic velocity u. What we will do now is try to find the time operators connected to these two velocities. So the first thing we do is to ask how these two velocities change with related to the time inversion operator, which is t. We know that the systematic velocity has to change its sign when we invert the sign of the time, but the systematic velocity we expect that preserves its signs, because if you have a stochastic behavior, it doesn't matter if you go with the time to positive or negative signs, directions. So if we do that, we can apply the operator t to the velocity c. Of course, it will change only the sign of the systematic velocity, and with this result, we can in fact express both the systematic and the stochastic velocities in terms of c and c prime. C prime is the result of the application of t over c. These two results give us the expressions for the systematic and stochastic velocities in terms of c and c prime. Okay, now we can ask. We are of course in quest of an operator like this, because this operator will enable us to find a dynamic equation akin to Newton's one, but now involving stochastic behavior. So we will try to find such an equation. So we begin with these displacements. Of course, it is needless to say that this has a lot to do with our previous derivations. And doing that, we can now express the change of any quantity f. We call f a function, any function of the position, which is the usual way. We apply f to the position displaced in time minus f and divide it by time. We know that this will give some approximation to the time derivative operation. So we express this by making this summation. This is of course the development in series of these terms delta q, which are here already presented, and we note the fact that the authors of this derivation assume that they will make this summation up to second order terms. Note that these can be expressed as delta Qi, this one is delta Qj, and we will have just second order terms in our up to second order terms in our expression of the variation of any function f with respect to time. Okay, this is important because this is exactly the same constraint that we are applying up to now. We then may do the next step. The next step is to take the average. This average is very important. It will have enormous consequences uh, later on. So we take these uh, averages and take the limit as delta t goes to 0. Of course, we want a derivative. So when we do that, we assume that this average of delta q with respect to delta t is just c, the velocity is natural to do that, and we use the letter d just to calculate this variation delta qj with respect to delta t. In fact, it is just a constant that we will try to find the value later on. So when we do that, we now assume that this constant can be expressed as a constant which is only diagonal and has the same value for all the terms. Then we express finally this derivation operator in terms of c, our velocity, general velocity, which encompasses both the systematic and the stochastic derivative, and this constant d. Okay, this is a first result, which is very important. We now may ask how this time derivative operator uh, responds to the time inversions. Then we can construct two operators, d here, which is just the one we have just constructed, and d prime, which is the time inversion of d. Of course, this time inversion, when applied to this term, changes the sign. When applied to this term, just change c into c prime. This term is not affected, of course, and this term is affected because we have a delta t here as we just defined it. Okay, we can now just write these two terms in a more simplified way as operators, and now we see that we can combine these two terms to find the velocities in terms of the derivative of the position and the two components, in fact, of the velocity. That is, we can just apply this first expression to q. Q is not a explicit function of time, so this term does not matter. We can apply here, which gives just c, it is presented here, and the same arguments apply to this operator. We have these two operators give 0, and when we put here q, we have just c prime. So we have these two results, and since we know that we can combine c and c prime to get the stochastic velocity and the systematic velocity, we do that, and we find that the systematic velocity is related to this uh, just subtraction of d and d prime, and the stochastic velocity is related to a sum of them. We note that in the limit when u is 0, this term, which is this sum, goes to 0, and the other one goes to the usual definition of velocity in terms of the derivative of the position. Okay, we now assume that our acceleration, this is just Newton's second law applied to a situation in which we have stochastic elements. We know it's not even it's not exactly Newton yet, because we don't introduce the force. We will do this uh, in a moment, but it's the beginning of the quest for a dynamical equation. We then express this general velocity in terms of the derivative of the general general acceleration, excuse me, in terms of the derivative of the general velocity, this time derivative, and we impose another constraint that this acceleration must be time invariant, which is the same case as we get with Newton's acceleration. So if we do that, and if we write here d as the combination of ds and dc, and here the velocity as the combination of the systematic velocity and the stochastic velocity. So here we use the combination of these two derivations, yes, systematic, we get the following result. Note that this term is invariant with respect to time inversion, because this changes and this changes, so it keeps itself invariant. This one does not change, this one does not change, as we have already noted. So it is also invariant, but in thus they are equal to the acceleration, which must be t invariant, but this other term is varies. So this term keeps itself, but this one changes. This one changes, but this one keeps itself. So we must set them equal to 0. This means that we end up with two equations for the time variation of the stochastic and systematic velocities. If we now make the association now related to Newton's second law, but to stochastic terms, between the acceleration and the force, an external force, we just get these two equations in which we assume that this force must be related to the usual way in which we associate the acceleration, which is just the systematic derivative, and some stochastic term with lambda to be determined. Okay, if we do that, we get two equations. Now we will express both d and ds, dc and ds, in terms of the expression they present. We have derived these two expressions, just have to sum d and d prime and subtract them, and we get these two equations here. Note that one is related to the velocity v, but it is also connected to the stochastic velocity. And the same we have in the other expression, and here we have the time derivative with related to the, the stochastic velocity, but it's connected to the systematic velocity. These two equations are connected together. Now we have to simplify these two equations, and we must write them in terms of d minus and d plus, which are combinations of these terms. We have expressed our force, external force, by means of a gradient. It's usual to do that. We are talking about potential force. So we may continue by now assuming the two expressions for the velocities. This is very restrictive. It is interesting to get to keep some notion of these two expressions, because these will be indeed the connection between this derivation and the previous derivations. Note that this v is just the gradient of s divided by m. Of course, we can pass m to this side, and we will have p as a gradient of s. Of course, this resembles a lot what we have already done. And look that if we use here the fact that we can pass these two to here, we just have the gradient of the logarithm of ρ, which is the entropy in our previous derivation, the entropy derivation. So we are connecting the stochastic force to the gradient of the entropy. We will talk a lot about that in the next video. Okay, of course, they can continue. And if we do that, we get now these two expressions. We can simplify these two expressions by assuming that the positive d and negative d are related to the same constant multiplied by an eta. And now we choose. This is another assumption of the derivation. This derivation has a lot of assumptions. We assume that the eta plus is 1, the eta minus is 0, and the plus goes to the 0, of course, because of this. And we also assume that lambda is equal to 1. There are reasons to do that, of course. What De La Peña and Cito are searching is the Schrödinger equation, so they are trying to make these two equations go into the Schrödinger equation some way. So by doing that and assuming these two expressions, which we have already talked about, we end up with these two equations. Note that this last equation, the second equation, for instance, we can multiply it by r squared. So we get here an r, we get here an r, and we get here an r squared. Here we can pass the r function to the derivative. We end up with dr squared dt plus 2r gradient of s with respect to m, and these r I can put inside the gradient, so we get gradient of r squared, and here I have r squared gradient Laplacian of s with respect to m equal to 0. This term is just an equation we have already found, which is just the continuity equation given by these results. The equation that we get here is just the usual equation we have been obtaining since the first derivation, if we put the constant d0 as h bar over 2 times the mass. If we do that, these two equations are just the two equations that we have already shown to be equivalent to the Schrödinger equation. And thus we finally get into the Schrödinger equation, and so derive it from the two notions of stochastic and systematic velocities, showing that some connection between the stochastic behavior and quantum mechanics must exist. This is the stochastic derivation. In the next video, I will show that there are deep connections between this derivation and the previous derivations. I have said something about that, but in the next video, I will show that in more detail. Thanks for watching.